Okay, so we're going to talk a little bit about redox and try to figure out how to do a voltaic cell lab here. So basically, a redox reaction is where something you have a reaction where you have transfer of electrons here. So one common example, you've probably seen this before in the lab when you do it in Chem 1 or maybe even intro. If you put a piece of zinc metal into some copper 2 sulfate solution here, which is blue. So the copper 2 ion is the blue color. And then what you'll observe happen over time on its own, it will form some dark stuff, solid forming over the zinc. And over time, your blue color is fading. Okay, so this reaction here is obviously spontaneous. It happens on its own whenever you put this metal into the solution, where what's happening is zinc solid here is turning into zinc ion. So they're basically switching places. And copper 2 ion here is turning into copper solid. That's the dark solid that you see appearing on zinc here. So over time, the blue color fades because the copper ion is changing into copper solid. And the copper ion is the reason why it's blue. So over time, you see the blue fading. If you wait long enough, your blue actually disappears. So if you remember this, if you guys took Chem 1 at SBC, we had an experiment in Chem 1 where you had to basically put aluminum metal into like a blue-green solution. Remember that? And then over time, the solution turned clear, and then you saw a bunch of copper forming. So we were doing that kind of same redox reaction there. That one's with aluminum and copper. This one is aluminum. This one is zinc and copper, okay? So basically the reaction here is, I wrote it down separately, but this reaction here, if you separated it into a cell where basically you had a component where you have one beaker or one side of it is zinc solid and zinc ion, the other side is copper solid and copper ion. If you connected it, you can actually make current flow spontaneously, and this is the basis of a battery. So it spontaneously will happen. That's what we call a voltaic or galvanic cell. This is the basis of a battery, basically having a spontaneous reaction. Once you connect the dots, electricity will just flow. Okay, so let me show you your equation here that we're talking about. So in this case here, we have zinc going to zinc 2 plus, copper 2 plus going to copper solid. So obviously this is a redox reaction. If you learned in Chem 1, we learned that this is oxidation state of 0, oxidation state of 2, oxidation state of 2, oxidation state of 0. If you can't remember how to assign oxidation states, this might be a good time to review over Chem 1 notes. Actually, if you're in Chem 2, the chapter 18 notes should be helpful. I also actually there's a slight review on how to do oxidation states. Okay, so basically, because this is oxidation state 0 going to oxidation state 2, this is an oxidation process. And then copper 2 plus is being reduced to copper solid, which is oxidation state 0. This is a reduction. So oxidation and reduction never happen without each other. They always happen together. Okay, if you have oxidation in the same place, there's reduction. If you have reduction, there's going to be oxidation. It doesn't happen without each other. So that's why we don't say oxidation reduction reaction. We just say redoxes for short. Okay, so we talk about half reactions here. So obviously there's half reaction for the oxidation side. So oxidation side, you have half of it. So where the story says zinc solid is somehow turning into zinc 2 plus ion. So this is aqueous here, not solid. Now, how did zinc solid turn to zinc 2 plus? The only way it did that was because it lost 2 electrons, agree? An atom, when you lose an electron, or 2 electrons in this case, you'll make cation or 2 plus charge. Because you lose electrons are going to show up on the product side, okay? On the other hand, you have reduction, where in our case here, copper 2 plus aqueous was turning into copper solid. Okay, so how did copper 2 plus turn into copper solid? Basically, it had to receive 2 electrons. You add the 2 electrons to the copper 2 plus, makes it a copper solid. So basically, you see a full circle. Zinc is releasing the electron, and if you force it through a circuit, the electrons will travel through and go to the copper beaker, and where the copper 2 plus beaker, and that beaker can absorb this electron and make copper solid. So this is the picture what we were talking about here, where the electron is flowing from zinc into the copper side. And once the electron hits here, the copper 2 plus ion takes it and makes itself turn into copper solid. On the other hand here, the zinc solid is turning into zinc ion. So you actually see that the anode here is actually going to change mass over time. It's going to get lighter. And this one's going to get heavier because you're depositing more copper on here and you're removing zinc from here. And your zinc concentration in here should actually increase. So it's really cool concept, okay? So basically, how in the world did they come up with this table here? And what does this mean? So they tell you, here's a table of reduction potentials. So they're all like numbers over here. And if you notice, these have electrons all on the reactant side. So that means, if I take a look at this, this means I have a reduction being written. If you have electrons on your reactant side, that means we're talking about a reduction equation. Okay, so this table here actually shows us a bunch of reduction equations and the potentials that are associated with it. So how much voltage? So this potential here is electron potential here. So basically they're saying like, they compare everybody to this 0, which is the hydrogen, standard hydrogen electrode cell here, half cell. And they're saying if this thing likes to be reduced more, it will have a positive value. The more it likes to be reduced, the more positive the potential is. If it doesn't like to be reduced, it actually has a negative value. Okay, so if it doesn't like to be reduced, it probably likes to be oxidized because oxidation and reduction are opposites. So basically, if they give you a table of reduction, right, and they don't give you a table of oxidation. So how do you get the values for oxidation? So in this case here, all you have to realize is oxidation is literally just the reverse. It's flipped. If you say this is reduced to that, this is oxidized to that. So lithium plus, add an electron is reduction, it's being reduced to lithium solid. On the other, so the potential would be negative 3.04 for reduction. Now on the other hand, if you want to talk about oxidation of lithium solid to lithium ion, you would say, well, it's going to here, you make lithium ion and you lose an electron. So it's like reverse. So when you reverse this equation, all you do is you change the sign of your E naught. Okay, so this is your reduction potential, but it's written for reduction, but you can easily find the oxidation values here by flipping the sign. So let's take a look here. If we had this here, so the rule is for this table here, all the concentrations has to be 1 molarity. The naught here signifies it's standard. That means it all has to be 1 molarity. If it's not 1 molarity, your numbers actually change and you have to use a different formula to calculate it. Okay, so we're talking 1 molarity here. So I have an oxidation and a reduction. And if I wanted to get the E of this cell, okay, which is what they're asking for in your lab, you would literally say, well, let me look up the values from the table. So I know reduction is copper 2 plus to copper solid. So you look on your table and you say, well, reduction has copper 2 plus going to copper solid, and my number is positive 0.34. So let me go ahead and write it down. So E reduction is E of, E cell is E reduction plus E of oxidation. And I just looked up the reduction value for copper. It was positive 0.34 volts. Okay, now the next thing is let's look for oxidation for zinc. This time, remember, we're looking for zinc going to zinc 2 plus, losing 2 electrons. So obviously they don't have a zinc oxidation reaction, they wrote in reduction, but you can see that zinc going to zinc 2 plus is the opposite of this line. So basically the number, instead of negative 0.76, the oxidation value would be positive 0.76. So you would say this is positive 0.76. And then you'll add it up, you'll get, in this case, 1.1. Positive 1.10. Okay, so hopefully this makes sense. So this is how you get the standard values. Okay, so what's cool is this is going to be transferred, and then the 2 electrons here we'll talk about later too. So this can be transferred here to our first scenario where we have a standard voltage. So remember, standard is 1 molarity. Non-standard is when the molarity is no longer just 1 and 1. There's different molarities here. So, so what we just did was we calculated the theoretical, or to calculate it from the value from the table. This 1.1 goes here. Okay, so that's our first cell here. And then if you wanted to get the anode and the cathode is basically where the oxidation happens. The solid where the oxidation happens, and cathode is the solid where the reduction happens. So what will be my anode here? Who's being oxidized? It would be zinc solid. And then my cathode would be copper solid. Okay, so the electrodes here have to be solid form. So you always just pick the solid that you were working with. Okay, so to get the percent difference here, all you do is you take the difference between that, and then you divide it by the theoretical times 100. So let's go ahead and try doing that. I'm gonna write the calculations, I guess, on a piece of paper over here. So basically, the percent difference for the first one, basically is the absolute value of my theoretical and my experimental, the difference between those. So 1.10 volts minus 1.08 volts, and then divided by 1.10 volts, and then times 100. That would give me the percent difference. So the difference here, I know the table and the before that sometimes they ask you for difference, but I think the quiz actually asks you for the percent difference. So 1.10 minus 1.08 is the difference. So you should get 0.02 over there, and then you divide by 1.10, and then times 100 to get the percentage, which in this case is 1.82%. Okay, so you would put that here. So not too bad. So all you do is you go through the list. This is 1 and 1, so standard. If you wanted to do lead and you wanted to do copper, all you would do now in this case is you have to decide who's going to oxidize and who's going to reduce. So what's cool about voltaic cell is your number must always be positive. If you ended up getting a number that was negative, you just did the opposite of voltaic cell, which is an electrolytic cell. That one doesn't happen spontaneously. You actually have to hook it up to a power source for it to take place. So I have lead and I have copper this type. So let's take a look at my chart. Okay, we'll take a look at this chart here on your lab manual, and you have to look for lead and you have to look for copper. So lead here is this value, negative 0.13, and copper is positive 0.34. So according to this list here, copper likes to be reduced, and lead, in this case, doesn't like to be reduced as much because it's a negative value here. Instead, it actually likes to be oxidized. So what happens is, what you should do is say copper is going to be reduced and lead is going to be oxidized. So you can't have both of them being reduced. You just can't do that. Both of them can't be reduction, both of them can't be oxidation at the same time. One has to be reduction, one has to be oxidized. So basically you have to flip one of those lines. Out of these two lines, if you flip the wrong one, your total will become negative. So then you know you just did the wrong thing. You want to make sure your total ends up being positive. So in this case, I am going to pick this guy to be flipped around, because I know that because copper is more positive value, it likes to be reduced. I'm going to keep it as reduction, and I'm going to go ahead and change this guy from a reduction reaction. I'm going to flip it and make it do an oxidation. Okay, so I'm going to write this out on the paper. Let's remember these values here. So the next cell here that we have was 1 molar Pb and 1 molar Cu. And actually told you it's Pb2 plus and Cu2 plus. It just wasn't in the table there. So it's 1 molar, and let me write out the values from the table again. So on the table, they wrote down Pb2 plus Aq plus 2 electron goes to Pb solid, and they say the E of this reduction process was negative 0.13 volts. And then the next one that we had was copper 2 plus Aq plus 2 electron goes to copper solid. And they said the reduction potential for this is 0.34. So the more positive the reduction potential is, the more that thing likes to be reduced. So who's being reduced is copper 2 plus being reduced to copper solid. And in the end here, because this tendency, this guy likes to be reduced less than this guy, what happens is lead is going to be oxidized. So lead is going to be oxidized to lead 2 plus, and the oxidation potential is therefore positive 0.34. I mean positive 0.13. Okay, so I can actually write my half cells. So I know I'm going to pick oxidation to be Pb solid equals to Pb2 plus 2 electron here, and my E of oxidation is going to be positive 0.13 volts. Okay, and then basically you have to reverse one and keep the other. So I reverse this guy, I have to keep this one, copper 2 plus EQ plus 2 electron equals to copper solid. So in this case here, this guy's value will be negative, positive 0.34 because I didn't flip it. So 0.13 and 0.34, you end up getting positive 0.47 volts. So that would be the value that you would put on your table. Now remember, if you accidentally flip the wrong one, so E cell right here, I should write it down. E cell is just adding E oxidation and E of reduction, because you can't have both oxidation. This one's reduction, this one's oxidation. Okay, you add them both together, you get E cell. So remember, E cell, E standard cell is E standard reduction plus E standard oxidation. So remember, oxidation is flipped from the table value because the table is only reduction values here, and then you add them up together. So this 0.47 here would go over here. Okay, and then you can do the same thing, get the percent difference by doing the theoretical difference, absolute value difference between theoretical and experimental divided by the theoretical times 100, and then you get your percentage which goes there. So let's take a look at who's your anode and cathode. So remember, anode is where oxidation is, cathode is where reduction is. So who's being oxidized? In this case, it would be lead solid. Who's being reduced? Basically, copper is being reduced. So the copper solid would be my cathode. Okay, so anode will be Pb, cathode will be Cu. So you just fill it up. Basically, the anode and cathode is a solid on each half cell, whichever half cell you end up. Oxidation is the anode, cathode is the reduction site. Okay, so that's that. That's for 1 molar. And if you take a look, you can continue this for this lead and zinc, and then you have aluminum and copper. So I will actually do one of these here, and then I'll do one of the aluminum and copper just to show you a little bit different. But I'm sure by now you understand how to do the comparing these values and how to fill in anode and cathode. Okay, so with this next part, because it is not going to be 1 molar, you actually can't copy the values from the table. The values from the table actually goes in the equation for you to find the E cell. E cell at not standard condition is without the little not sign. E cell equals to E naught cell. This will be what you calculate from the table, minus 0.0592 over N. There is a different equation in the manual. It's like, it has RT and all that stuff. Basically, that equation is the same as the one I'm giving you. This one here is specifically made for 25 degrees Celsius, which they're telling you assume this experiment is at room temperature, which we do it at room temperature. So if you do it at room temperature, you use the simplified equation, which makes it a lot easier. The RT and F is a lot longer, more numbers to plug in. In this case, it's log Q instead of ln Q. Okay, so wanted to show you guys how to do this. So what in the world is N? N here is the number of moles of electrons when you do full circle. So in this case here, if you notice, zinc and copper, zinc and copper here, the full circle, when this one loses 2 electrons, this one takes in 2 electrons. So full circle, this one leaves 2 electrons, goes out, this one takes the 2 electrons. So the full circle N here, number of moles of electrons will be 2. N would be 2 in this case. Now, if you take a look at this experiment here, this one here says lead gives off 2, copper takes 2. Again, the N is equals to 2 in this equation. Okay, so that would be pretty simple. We could do N is 2 for those two cases. Now, aluminum and copper is going to be a little different because aluminum has 3 electrons coming off and copper has 2. 2 and 3, the common number that you'll use is end up being 6. I'll show you the example for aluminum and copper. But let's go ahead and try, I'm going to go ahead and try the first one here and the last one just to show you the difference. The other video should actually be working out more examples to show you guys as well. But let's go ahead and do that. So copper and zinc here, because it's not 1-to-1, it's 0.1-to-1, I'm going to have to calculate a new E cell, but I have the E standard from before. The E standard that I just calculated earlier, I said it was 1.1. So I'm going to go ahead and say this is positive 1.10 volts minus 0.0592 volts. This is actually in units of volts here. And then over N, we just talked about it. N is the number of electrons that you use when you combine. So the number of electrons have to be the same number, okay? So in this case, this is 2, and then log of Q, and you're like, what in the world is log Q? Q is basically products over reactants for the concentrations here. Kind of like Q and K, remember that? So we have to get Q. So let's take a look at what Q would be. My equation here was right here. I knew that zinc was going to zinc 2 plus, which was that. And then copper 2 plus was going to copper. And you want to combine them. So when you combine them, you have this as a reactant and this as my product. And you don't write the electrons because they cancel off. That's why you have to make sure they're the same electron count. Okay, so let me write the equation out. Again, this is the equation for zinc solid plus copper 2 plus. And then that goes to zinc 2 plus aqueous plus copper solid. Okay, so here's my equation here. And remember the molarity was given in this chart here. It says 0.1 molarity copper. So this is 0.1 molarity here. And zinc here is 1 molarity. The solids, you don't need molarity because you don't even write it in. So in this case here, the Q would be zinc 2 plus concentration because you don't write solid products over the reactants, copper 2 plus on the bottom. So the log of Q here would literally mean the concentration of zinc, which is 1 molar, and then divided by 0.1 molar. So 1 over 0.1, and you can get your answer there. So obviously, for the second one, you will replace this 0.1 with 0.5 right here because the copper concentration now is 0.5. The N would still stay the same as 2. So calculation becomes really easy. Okay, so let's go ahead and try to do that. So the molarity here is 1 over 0.1, which gives me 10. Log of 10 is then 1. So, well, that's nice. So log of 10 is 1. 1 times this basically is the same thing. So what you get is 0.0592 over 2 times 1, which is the same value here. And then you get, that's negative. So let me write it out. So this is 1.10 volts minus 0.0296 volts. Okay? And then you get 1.07 volts. So that 1.07 goes over here. Okay? So that's what you would get. You'd be able to calculate it. Now, if you wanted to do, remember, if you wanted to switch it to the next cell, all you do is you switch that to 0.5 here. So 1 over 0.5, you end up getting 2 log of 2. In this case is 0.3. So that would just change that a little bit. So obviously this value will change a little bit, and then that stays the same, and you'll get a different value over here, and that goes over here. Okay, so and you can do the percent difference the same way like earlier. And obviously the anode and cathode stays the same like the standards. It stays exactly the same. Okay, so that's how you do for the copper and zinc. Now, all of these here are going to be two electron system, except for this last one. So I want to show you the last one because it's going to be a little bit different. So for the last one, obviously, I need to do the standard cell for the last one so I can plug it into my equation for one of these guys. So I'll probably do the last one over here for you guys. Okay, so let's go ahead and do the standard for aluminum and for copper. So aluminum and copper, I'm going to write out, let's take a look over here for standard conditions. Aluminum is this value here, aluminum 3 plus going to aluminum solid, and it's a negative 1.66, so I know this guy doesn't like to be reduced. What about copper? Copper is copper 2 plus to copper, copper is positive 0.34, so copper likes to be reduced, and this is a negative value, so it doesn't like to be reduced. That means I need to make sure it goes to oxidize. Okay, so basically you flip the smaller number, you flip the more negative number always. And that should always give you the correct answer. That's how you would end up getting a positive value for each cell. So in this case here, let's go ahead and do my E cell. So I guess I'll go ahead and write it on a separate page here. So we have aluminum. I'll write down the values from the table. So aluminum 3 plus 3 electron, it goes to aluminum solid. And this one, the E of reduction given was negative 1.66 volts. And then again, we have the copper 2 plus 2 electron goes to copper solid. This is aqueous, don't forget. This is positive 0.34 volts. Okay, so I know that I am going to go ahead and keep copper as reduction, copper 2 plus reduced to copper solid. So I'll write the reduction half as Cu2 plus 2E goes to Cu solid. And then my E of reduction is given as positive 0.34. I'll do the same for oxidation. So oxidation here is going to be the opposite. I know aluminum is going to go to aluminum 3 plus 3 electrons here. And E of my oxidation in this case is positive 1.66. I had to flip the reaction, so I have to flip the numbers. So in this case here, 1.66 plus 0.34, you're going to end up getting 2.00 volts, and it's positive. And you're like, whoa, this is a really big difference. But that's okay. Sometimes the cells have big difference because there are side reactions happening during the lab. So that 2.00 here goes into over here. Okay, so I'll go ahead and fill it up, might as well. And then over here, can you tell me who's being oxidized and who's being reduced? So aluminum is my anode, copper is my cathode. So aluminum solid is my anode, copper is my cathode. And then you guys can do the percent difference here. Now I'm going to take this value. This is my E naught cell, and take it into the reaction that I don't actually want to do. This was for 1 molar, but I actually want to do the system where I have 0.5 molarity of copper versus 1 molarity of aluminum. That's the cell I want to focus on. And remember, E cell that is not standard equals to E standard cell minus 0.0592 volts over 2 electrons log of Q. So I have to get Q, oh no, that's not 2, like this is N. Okay, so that's N here, number of moles of electrons. So again here, number of moles of electrons, we have to take a look at the full circle here. Can you combine these two as is? You can't, because the number of electrons don't match. So what you have to do is multiply the top line by 3, multiply the bottom one by 2, and you make both sides go to 6 electrons. So I'm going to rewrite it, okay? So the copper is going to be multiplied, the reduction is going to be multiplied by 3. This one will be by 2, right? So let's go ahead and write that. So I'll get Cu3 Cu2 plus 6 electrons goes to 3 copper solid. Now, one good thing about this E cell stuff here is it's an intrinsic property. If you multiply these all you want, you don't have to change that at all. So that's great. That works out for us. We don't have to change that because I know that's going to go right there. Okay, so we have this equation here. We multiply that by 3. So let's do the bottom one multiplied by 2. So this is my reduction, and we want to do the oxidation. it will be 2 aluminum solid goes to 2 aluminum 3 plus equals plus 6 electrons. Perfect. So now I have 6 and 6, then I can combine them together. So basically this is all my reactants, this is all my products. My overall reaction is 3 Cu2 plus. You don't have to write electrons because they cancel off, plus 2 aluminum solid goes to 3 copper solid. Oh, solid. You don't have that 2 up here. Okay, plus 2 aluminum 3 plus. So I have that, and now I can write the Q. Q for this guy is actually going to be aluminum 3 plus concentration, right? But there's 2 coefficient here, so that's to the power of 2. And then on the bottom here is 3 Cu2 plus, so concentration of Cu2 plus to the power of 3. So that's the difference there. Earlier, we didn't have to multiply the coefficient, nothing at all. So everything was 1 to 1. Literally, you didn't have any power. But if you didn't do this guy here, you'd be in trouble because your Q is very, very different. Okay, so now that you have our molarity value from here, you can plug it into your Q here. And you know that your N here is 6. Okay, so we'll plug it in back into the equation. So E cell is E naught cell, which we calculated earlier, it was 2.00. It was positive 2, and then minus 0.0592 over 6. This is also volts, okay? And log of, so this is aluminum's concentration, which was 1. So 1 to the power of 2. Copper concentration was 0.5, and you have to take that to the power of 3. Okay, so let me zoom out a little bit so you can see more of the page. Okay, now once you have this here, we can go ahead and solve for it. So let's see. So 0.5 to the power of 3, 1 divided by that, log of that value. So that value gives you 8 here. So log of 8, you get a value which is 0.90-ish, 0.903. And then you take that, you multiply with 0.0592 over 6. And that's a negative value plus 2. So I get my answer to be 1.99. Okay, so you just make sure you know how to do this on your calculator. If you have trouble, remember, do this one as a number. 1 squared, which is 1, or do that divided by this value on the bottom here. Make sure you're putting in brackets. You should get about, what was the number? You should get 8 for this value here, okay? And then you'll log of 8, you get like 0.9, and then you multiply by this value, and then 2 minus this whole term, okay? You should get 1.99 there. So go ahead and put this over here. And then you can do the difference, and the anode and cathode, again, is the same as what's above. So I hope this helps. It is a lot. This equation is called Nernst equation. Now, I like to use this equation because we're keeping at 25 degrees. It makes things a lot easier rather than having to use a Faraday's constant and all the other units in there, like gas constants and stuff. Okay? All right. So I hope this helps. If you have any more questions, let me know. But this is the part to the results. Oh, yeah. I wanted to show you guys how to answer the post-labs as well, actually. So the post-lab question is right here. Print out some examples here. It says you will probably get a different number. You just auto-regenerate. So a metal is used as a sacrificial anode where the effect is to reverse the oxidation. So you don't want iron to oxidize to iron 2, but you oxidize X to X ion. Okay, so calculate the voltage if this reaction takes place under standard conditions. So that was nice. The standard reduction potential of X is 0.8, so negative 0.8. So basically they're saying X reduction is negative 0.8. So X reduction, we don't know how many electrons, we just pretend it's like 1, I guess. It doesn't really matter in this case. So X plus electron goes to X negative, right? And they say the E of reduction for standard condition was negative 0.86. 0 volts. Now, you want to compare this and you say you want this to oxidize. Okay, so you want it to actually, so it's plus here. So in this case here, is X plus to X solid. Okay, so and then we'll say iron 2 plus value. So I'm going to copy the iron 2 plus value. Do we have the iron 2 plus? Yeah, we have iron 2 plus value here. So plus 2 electron goes to iron solid. The reduction given was negative 0.45 volts. So they're saying take this value and compare it to the reduction. So in this case here, I have to make sure I flip the more negative one. So obviously they also told you to oxidize X. So X here would be oxidized. So oxidation would be positive 0.80 volts, right? And a reduction value would be negative 0.45 volts. And then you add them up, you get the E cell, which would give you 0.35 volts. Okay, so all you do is you compare the value that they gave you, flip that one, compare it to iron. Okay, so we'll make sure this one's being oxidized. Now the next question here is going to be a Nernst equation, and they tell you to assume it's 25 degrees, which is great. We can use this equation here, and you'll have to do zinc and metal to X2 plus, and they say the reduction potential of X is 0.23. So basically, we have to look at zinc. I'll write it out. So 0.6 molar zinc compared to 1 molar X. That's the cell that they're talking about. And then we have to figure out who's the anode, who's the cathode, and all that stuff. So when you take a look at the zinc here, zinc and zinc 2 plus, so zinc's value, zinc 2 plus 2 electron going to zinc solid. The value from the chart here we have is negative 0.76. So this is E of reduction, okay? And they're saying the reduction of X here, X2 plus 2E, from this question it says going to X is 0.23 volts, okay? So in this case here, one's a negative, one's a positive. So I'm gonna say this guy is gonna reduce, that guy is going to oxidize, okay? So the zinc is going to oxidize here. So my E of oxidation is going to be 0.76 positive value. My E of reduction is 0.23 volts. So I should get a value of 0.99 volts. Okay? Now, I have to also go ahead and write out the equation so I can see what the Q is. I can see here clearly my N is 2, but let's go ahead and write the equation. So the equation here is I'm going to oxidize zinc. So zinc goes to zinc 2 plus 2 electrons. Reduction goes to X2 plus 2 electron goes to X. Okay, so that's my reactant. That's my product. So I can combine acids because N is 2. Q in this case is going to be zinc concentration 2 plus over X 2 plus concentration. Okay, so you would put in E cell equals to E standard cell, which is 0.99, which is calculated at minus 0.0592 over 2 log of zinc, which is 0.6. X is 1. Okay, and that you should get your answer. So let's double check. 0.6 log of 0.6, and then times 0.0592 over 2, and then negative f plus 0.99. You get like 0.996, like so small, but it rounds out to basically 1.00. So I would round it up. 1.00, because I think they say to 2 decimal places here. So, okay, so I hope this helps.